Okay, we'll talk about systems of linear equations. Now, remember that an equation is the application of a rule. So every pair of numbers which satisfies that equation satisfies the rule, the underlying function. Now, you may well have many different rules. You may have, therefore, many different conditions that have to be satisfied. And it's precisely in analyzing problems with many different rules that need to be simultaneously satisfied that we use systems of linear equations or simultaneous equations. Actually, systems of equations, they may not be linear. Today we'll just talk about linear ones. Okay. So here we've got two equations, y equals 4x minus 14 and y equals x plus 5. I guess these are the equations we just worked out. Solving this set of equations, we're just going to do an example with two, but there could be any finite number of equations that we might need to solve. Solving means finding the values of x and y, that's the pair of x and y, such that both equations are valid. Okay? So when we're talking about linear equations, there are just three possibilities. That is, there's a unique solution. When we're talking about linear equations, and we're only talking about two equations, no more than two, then there's either a unique solution, that is, the two lines cross at exactly one point. Because they're linear, they can only cross once. It's possible that they never cross. And why might that be the case? Why might they never cross? Yes, what's your name? Same slope. Same slope. So they would be parallel lines. Or there are infinitely many solutions. That is, the two lines happen to be exactly the same. They coincide. It may not be obvious when you look at the equations that they're the same, but when you plot out their graphs, you'll realize that they are the same. Okay? So the happy situation where you have two equations that cross once with a particular solution, let's say the solution is x star and y star. Okay. X star refers to a particular value of x, y star refers to a particular value of y. Okay. Okay. This is generally the kind of problem we're trying to solve. Okay. The graphical method of solving works only when there are two unknowns, and therefore two equations. You simply graph the two equations the same way that we've done so far, and you look for the values of x and y where they intersect. So x star and y star, this is the point of intersection. And here is the solution for the two graphs that we just worked out in the previous section. Okay? Okay. Of course, it's not convenient to always use the graphical method, so you might need to substitute. And so the substitution method is really a process of elimination. What you do is you solve one of the equations so that you have either x or y alone on one side. So you're expressing x in terms of the other variable y, or y in terms of the other variable x, and then you substitute that expression for x into your remaining equation, so that you end up with one equation in one unknown, and you all know how to solve that algebraically. So a common technique in mathematics is always to take a complex problem and to reduce its complexity by one level, and then to take that simplified problem and reduce the complexity by one level, and so on, by a process of iteration. Okay, 2,000 years ago, people took a lifetime to do this sort of thing. Nowadays, we have Excel or MATLAB or other iterative programs. Okay. Okay, so here we're simply trying to solve the two equations, these two equations, this one and that one, via the substitution method. Okay, so we've got y equals 4x minus 14. We actually don't need to do anything here because we've got y expressed in terms of x. There's no y on the right-hand side. So we could simply take this expression and substitute it into the other equation. The other equation is y equals x plus 5. So instead of y, I have here 4x minus 14. The reason we've put the star here is to indicate that this equality only holds for a particular value of x which satisfies both equations, i.e. this x star here, right? So here I'm solving for a particular value of x, which is called x star, and I just algebraically manipulate till I get x star is equal to 6 1/3. Okay? And then I could substitute x star back into either into this equation or that equation to get what y star is. So let's do a quick application, quick and simple application, and then we'll talk about more interesting things. Okay, so a very common problem is supply and demand. In economics, we very often describe the quantity supplied and the quantity demanded in a marketplace as a function of price. Price is the independent variable, the input variable, and quantity demanded or quantity supplied is the dependent variable, the output variable. Now, so far, this is a quirk that you should get used to. So far, I have always displayed y on the vertical axis and x on the horizontal axis. And x was the input variable and y was the output variable. For historical reasons, economists have always shown price on the vertical axis, even though it is the input variable, and quantity on the horizontal axis, even though quantity is actually the output variable. Okay, so generally, all supply and demand curves that you will see look like this. This is a demand curve, and this is a supply curve. And price is actually the independent variable, and quantity demanded or supplied as a function of price is the dependent variable. Okay. So that's why the way this is, shown, the way I've expressed this, Q as a function of P, shows the underlying functional relationship, but Q is not on the y-axis. Okay? This is just a quirk that sadly creates all sorts of confusion, so it's just something to watch out for. Okay. So here, suppose that we have a demand curve. Quantity demanded is equal to 300 minus 6p, and quantity supplied is equal to quarter p. Okay? All the intuition that I gave you earlier about a steep slope and a shallow slope has to get reversed because of this problem, because this really is a mirror image, a transformation. So look at this. This is minus 6p. It would look like a very steep negative slope, but when you draw it, because the axes are reversed, it will look like a shallow negative slope. Okay? Okay. When you try to solve this, you won't have to worry about that. You won't have to worry about the geometric intuition. You simply carry out the process of substitution which we talked about earlier. Okay, so let's see. So suppose that we have this demand function and this supply function, and we want to find the point of equilibrium. Well, we can simply set the demand function equal to the supply function, QD equals QS, and solve for P, or rather P star. We get a value for P of 48, a value for Q of 12. And we don't have to worry about what that looks like. Okay, so yes, any questions? No? Okay, good. Okay, I think we're doing very well here, so we're probably going to finish early. We're going to talk about nonlinear functions, and okay, so this is a repetition of a slide from earlier on. By definition, a nonlinear function is one whose slope changes for different values of x. By definition, a linear function is one whose slope is constant. Okay? So this is a nonlinear function. This is a linear function. Okay. Now, in nonlinear functions, the slope is constantly changing. And in order to carry out analyses about nonlinear functions which have constantly changing slopes, we could simply do graphical analysis. We could simply, if we knew the equation of the nonlinear function, we could draw a graph, we could plot a graph and find out its behavior, and that's one of the things that you do before you start doing calculus. But because we can't always do that, we use calculus as a shorthand for describing how the slope of a nonlinear function changes. Okay, so calculus liberates us from having to use graphical techniques to describe the behavior of nonlinear functions. Okay, so think of calculus as a set of rules that tell us, that provide a shorthand for how the slope of a nonlinear function changes, because we know that it is constantly changing. Okay. Okay, examples of nonlinear functions, a power function, okay? A power function is a function which has a constant power or index for c. This need not be an integer. It could be 2 or 3, or it could be 2.3. So c here could be 2.3, and that would be a power function. Okay? An example of a power function here is a cubic function, 2x cubed. Okay? A polynomial function, one I'm sure you've seen many times, a polynomial, let's say, of order 4 would be something like ax to the 4 plus bx to the 3 plus dx to the second plus x plus c. Okay? And here is an example of a polynomial to order 2. Okay. An interesting function that we will use often in many scientific applications and also in many financial and economic applications is the exponential function. Any function that has x as an exponent is an exponential function. So, for example, 2 to the x would be an exponential function. The one exponential function that I've given you here is a particularly special exponential function called e to the x. And e, anybody here know what e is named for, or who e is named for? Not Einstein, but someone older than Einstein. No, not that old. Euclid is a good try. Not that old. Leonhard Euler, who actually I mentioned earlier, is the first one to define mathematical functions. Okay. What is e? Anybody know what that number is approximately? 2.71, right? To 2 digits. I actually don't know what the next digit is, but okay. The logarithmic function, you probably all, when you did mathematics in high school, I don't know if they still teach log to base 10 in high school. You probably won't know that either, but this is not log to base 10. This is the log to base e, or the natural log. Okay? The log to base 10 is not very useful concept nowadays because everybody uses calculators. Log to base 10 was often used when people didn't have calculators because it's a fast way to do multiplication and division. Okay, so here is the exponential function. You should get used to what this function looks like. So e to the x, when x is equal to 0, is 1, because any number raised to the power 0 is equal to 1. Okay? So the y-intercept is equal to 1. It is an exponentially rising function, so you'll see that its slope increases as x increases. Okay, so it has a shape similar to other exponential functions. It has the feature that its inverse is equal to the natural log function, and you should get used to this shape too because it's very useful in many applications. And here you'll see that it starts off at minus infinity for x equal to 0 and rises, but unlike the exponential function, its slope gets more shallow as x increases. Okay, so that's a useful point to start thinking about inverse functions. Okay, so what's an inverse function? Remember I said that a function is a rule. It assigns an output to an input. One thing that I left unstated is that it assigns a unique output to an input. Okay, so it assigns a unique value y to each value of x. It doesn't mean that each value of y has associated with it a unique value of x. Okay, so that means that two values of x could lead to the same y, but one value x is only going to give you one y. Everybody see that? And pictorially, okay, so let's say this is the number 10. So if you give me an x value of 2, I'm going to give you a y value of 10 and only 10. But if you give me another x value, I might also give you 10. Whatever x values you give me, I'm only going to give you one associated y value. But if you were to give me a y value, I may give you more than one associated x value. The definition of a function, and that's why a function is not necessarily two-way, right? A function is a rule that takes x as an input and gives you a unique value y as an output. Now, a monotonic function is one that's always increasing or always decreasing. Is this a monotonic function? No, right? It's sometimes increasing, sometimes decreasing. So a monotonic function would be one that looked, for example, like that, such as the log function that I just showed you. Okay, now for monotonic functions, you could think of them as two-way rules, because if you have a monotonic function, for every value of y, there is only a single value of x that is associated with it. Okay? Now, the rule that assigns that single or unique value of x to every value of y is called the inverse function. So you could think of the inverse function as the rule that reverses the effect of the original function. So we started out with the function 2x. That's a rule that says give me x, multiply x by 2, and I'll give you an output equal to 2x. What's the rule that reverses that function? Yeah, x over 2, right? Half x. Okay? So if y is equal to 2x, then x is equal to y over 2. So I just switched the notation so as to keep it simple, so as to keep x and y in the same domains, but you could certainly say x over 2 also. Okay. Okay. Now, is there an inverse function for the function y equals x squared? I'm sure you remember this dilemma from. So, anybody remember the graph of x squared, right? This is x squared. Okay. So, what's the inverse of this function? Okay, so we have one vote for square root of x. Any other? Okay, so x square root of y. Okay, so that certainly reverses the process of squaring. It could be minus, right? So remember, this is not a monotonic function. So the natural inclination to reverse the rule doesn't work in this case because we don't have a monotonic function, because there are negative, for x in the negative domain, they also give you this x squared. So you can't simply reverse it, because remember, for an inverse function to exist, it has to be that for every value of y, I have only a unique value of x. So here, I now have two potential values of x. So when I take the square root, there are two potential roots, right? There's a plus and a minus root. So taking the square root is not actually a function, since it gives me two answers, two potential answers, right? And so that's why an inverse function doesn't exist for x squared. And so, you know, and you might say, well, this is arcane, you know, why do I care about this? But the kinds of places you'll certainly see it used, but I'll give you a flavor for it now. Generally, when you observe phenomena and you think that there's some relationship between one phenomenon and another, you will be in situations where you only observe one phenomenon and don't observe the other. Okay, so for example, you'll only observe y and not x. And so you'll have to surmise what x might have been. If you are sure about the rule, the function, then you're able to work out an inverse, then you will be able to surmise what that x is. If you are in a problem where there is no inverse because there are multiple ways of getting to that y that you observed, then you won't be able to conclude the presence of x just by observing y. Okay, so this looks very dry and technical, but it has very real example. Very real applications. And another, you know, a place where you see this a lot is, of course, in law, right? So this is directly related to the prosecutor's fallacy. If you see, you know, if you see some set of acts which are circumstantially linked, then you think that a certain person has committed a crime. But in criminal law, of course, you have to have a very high standard of proof, and it may well be that there are a number of potential hypotheses which are correct. That would be exactly the same as not having an inverse function, multiple x's that give you the same y. Okay? And that's exactly how it is used in science. And you'll see that hopefully in your classes. Okay? Okay, let's keep going. So the inverse function, I had given you the exponential function and the log function. These two are related in that the natural log is the inverse of the exponential function, and vice versa. Okay? And you can see this when you put the two next to each other. Just imagine for a second that I would have if I would have stripped this white square out from the screen out this way. So I would to take this point and put it somewhere here. This is not, you pull it out towards you, okay? And then I would to turn it around so that the x ended up here and the y ended up down here. Of course, this would end up looking just like that. Notice that this crosses the y-axis at 1, this crosses the x-axis at 1. Okay? And this goes off towards minus infinity, as does this. Okay, this is actually this is not drawn at y equal to 0, which is why this looks like it's touching, but it shouldn't be touching. In other words, the height of this is not 0, it's something higher than 0. Okay? Okay. Quickly, an implicit function. Very often, and this is more of a computational problem rather than a semantic distinction like the one between the inverse function. An implicit function usually, and so far we've defined all functions explicitly. That is, y is equal to x squared plus x minus 10, let's say. But sometimes you will have two variables related in a very complex way, and it's difficult to take one of the variables and put it on one side and strip it away. So you might have something that looks like this. This is a function of x and y. This is an expression that includes x and y, and that's equal to a particular number. So you'd have to put y on one side or x on one side, but if you did that, if you tried to do that, you'd have to solve a third order polynomial for y and a second order polynomial for x. So you'd end up with a complicated expression on the right hand side with many roots. And of course, as you know from our discussion about roots, roots don't have unique values, and so you wouldn't end up with an actual function. Okay? However, this condition nevertheless defines a set of x's and y's which meet that condition. Okay? And very often they will have some graph, even though that graph may not be the graph of a function. A very common implicitly defined function is anybody know what the graph of this implicitly defined function looks like? A circle, right? Okay, so that's not a function. For any value of x, I have two potential values of y. It certainly doesn't have an inverse. I have the same problem. But nevertheless, this condition is useful because it limits the sets of paired x, y's which satisfy that condition. And so once again, you might observe phenomena in the world which satisfy this condition. It may not follow a functional rule, but it tells you, or it limits the set of observations that you might expect to see. Okay? Okay, so keep implicit functions in mind. Once you have calculus, you are able to do some things with implicit functions. In particular, you're able to determine rules which tell you what the slope of that locus of points is at a particular value of x or y. Okay, and that may be a useful piece of information.